Okay, so we will speak today about a roller coaster and we will solve for the 8 here that I will call H, okay, for a roller coaster with different loop, okay, they all have the same age. Let me call this age of the loop, okay, so we got the name, they all have the same age, but they don't have the same row. So row 1, this one is smaller, row 2, and this one is larger, probably, let's say, let's put it there, row 3. Okay, so in my example 1, row 1 equal of the age of the loop divided by 2, row 2 is equal to the age of the loop divided by 4, and row 3 equal 2 times the age of the loop. Okay, and you probably, if you have seen some roller coaster, you know that the loop that we see the most often is this one, and I will explain you why. Okay, I will make some assumptions. I will make the assumption that the velocity here, the initial velocity, oops, let me make it a little bigger, is v0 equals 0. Okay, it doesn't change the fact that it will be easier to go through the loop 2 than the loop 1 than the loop 3, but I will show you why using the fact that this first velocity is 0. Okay, so to find h, so we want to find the minimum h. Okay, so the minimum h is when at, let's write it at point B, at B, the roller coaster stay on the track. Okay, so the roller coaster does not leave the track. Okay, so for when at B, let me write it, the roller coaster does not leave the track. Okay, so we can solve when it's about to leave. Okay, and that's the limit. Okay, so using this information, we will find the minimum, the VB mean. Okay, so the initial, the acceleration there will depend on VB. So let's do a little, I will show you, I will do a little free body diagrams and kinetic diagrams when the roller coaster is there. Okay, but let's make it bigger. Okay, so that's my roller coaster. Here we go, there. Okay, and that's my kinetic diagram. Okay, and we have someone inside. Oops, very happy to be there. Oops, same time. Okay, so we are on the top of the loop here. Okay, so which forces do we have? So that's the free body diagrams, and that's the kinetic diagram. What we have the weight, okay, and we have a normal force. Okay, we have a normal force because there's some contact with the track there. On this side, on the kinetic diagram, what we have is MAT, the tangential accelerations, and MAN, the normal acceleration, right? So that's my axis N. Let's just look at MAN. Let's just look at this. So we have sum of the forces on N equal MAN, okay? Because we want to solve for the VB minimum, it's when the normal force is 0, when it's about to leave the track. So we have W equal MAN. What is AN? Okay, the normal acceleration is V squared divided by rho. Okay, so we have mg equal m that's the V at B, VB square divided by rho. Okay, so I can simplify by M. So I have G times rho equal VB square. So VB it's equal to the square roots of G times rho. Okay, so that's the general formula. So first step. Now let's use the conservations of energy. So T at the point A, let me call this the point A, TA plus the VGA, the potential energy from the gravity, it's equal to TB plus VGB. Okay, so we need TA, we say that V0 or VA equals 0, so this is 0, plus VGA, so we need a datum. Let's put the datum there. Okay, so that's the datum, that's the 0 for the potential energy. Okay, so VGA, it's equal to W, and it's plus because it's above the datum, W times H, this H, it's equal to TB, it's equal to 1/2 of MVB square plus W time the H of the loop. Okay, let me call this HB. HB. I have some HB. I have some. Okay, H loop HB. That's the same. Yeah. Plus HB, and it's plus because it's above the datum too. Okay, so we have MGH. W is MG time 1/2 of M VB square. We have it there. Let me put it in golden. VB square it's equal to G times rho plus MGHB. And we can remove mg, mg, mg. Okay, so we have h that is equal to 1/2 of rho plus hb. Okay, see how the formula simplify a lot, and we have just this one left. Okay, so now we have 3 scenarios. Okay, so now loop 1, a rho 1 it's equal to, we say hb divided by 2. So h it's equal to 1/2 of hb divided by 2 plus hb. So h, so this one is 1/4 equals 5 divided by 4 hb. Okay, so we need 4. Okay, so let's say hb equal 40 meters. H should be 50 meters. Okay. Second scenario, loop 2. Rho 2 it's equal to, I say hb divided by 4. So h, so I use this formula, h equal 1/2 of rho, and rho is hb divided by 4 plus hb. Okay, so this one is 1/8, so we have h is equal to 9 divided by 8 hb. So now if hb equals 40 meters, h will be equal to 45. Let me just be sure. 45 meters. Okay, so if hb equal 40 meters, h in this case equal 50 meters. In this case, h will be equal to 45 meters. And loop 3, rho 3 equal 2 hb, so 2 times the 8 of the loop, so h equal to 1/2 of hb, of 2 hb, sorry, 1/2 of 2 hb, so one, that's from this formula, so 1/2 of rho, so 1/2 of 2 hb plus the hb, so h is equal to hb plus hb equal to 2 hb. So now in this case, h, if hb equal 40 meters, h should be equal to 80 meters. So you see, for the same hb, for the same 8 of every loop, in one case we need only 50 meters, 45 and 80 meters for there. So now you know why the loop of a roller coaster has a radius of curvature that is small. And that's what they look like this most of the time. And we have probably more force, more sensations on those loop, but you can have more loop, okay? Because for sure you lost a little bit of energy loops after loops, okay? And there's no motor on your roller coaster, so you begin at a very high height, and after that you just go down and down and down a little bit. So that's how roller coaster works. And that's it. So I hope you enjoy. Bye.